Hi, and welcome to this talk. I'm Steinþór Steingrímsson, and I'll be presenting the paper CombAlign, a tool for obtaining high-quality word alignments by myself, Hrafn Loftsson, and Andy Way. CombAlign is a simple tool that runs multiple word aligners and combines their output in order to get more accurate results, better precision, better recall, and a better F1 score, and a lower alignment error rate. But first things first, word alignment is the task of aligning corresponding words from two sentences in different languages. On this slide, we see a simple example of that, a short English sentence and a short Icelandic translation of that sentence. We can find correspondences between all words in the sentences. This is not always the case. It's actually probably more of an exception. But in this example, we can see that the task is not straightforward. Multiple words can align to one word, and the order of words is not necessarily the same in both languages, so alignments can cross, as we see in the example with don't run and hlaupa ekki. But why do word alignments? Why do this? Well, word alignments were a key component of statistical machine translation systems. I say were because SMT is used a lot less now than before. Better NMT systems are taking over. But even though word alignments may not be as important for machine translation as they were, they are still being used for various tasks. On the slide, I list a few recent or recent-ish papers. Word alignments can be used for bilingual lexicon induction, learning translation lexicons, for scoring sentence pairs when filtering parallel corpora, for helping with analysis and evaluation of translations, to preserve markup in machine translation texts um, or machine translated text. And in the paper, there's further discussion on more different use cases. So, as I said, in MT, machine translation, historically word alignments were important and thus quite a lot of work has been done in the field. There's a variety of word alignment tools available. Probably the most well-known is GISA++, which is about 20 years old. GISA++ is based on the IBM alignment models, which are statistical models using lexical translation probabilities and were the basis of MT systems for a long time. And then there is FastAlign, also based on the IBM translation models. This one has become quite popular. It's a lot faster than GISA++, and it can get similar and sometimes better results. The models by Robert Östling using a Bayesian extension to the IBM models are called FLOMAL, efficient low memory aligner, and FMARAL, efficient Markov chain word alignment. And these are also quite good. Recently, two aligners based on contextualized embeddings have been published. CombAlign came late last year with a paper published at EMNLP. It gives very good results and shows that word alignments obtained from multilingual pre-trained language models can be superior to strong word aligners like FLMAL, even in high resource scenarios. Awesome is brand new. It was published a couple of months ago with a paper on EACL. It learns alignments by fine-tuning MBERT on parallel corpora, and this aligner was actually published after we had our paper accepted. And it's not discussed in this paper, but I have tried it and it gives really good results. So we have these types of aligners. On the one hand, the aligners using the IBM models, and on the other, aligners using contextualized embedding models. These are very different methods, and thus we can expect to get different results. Hopefully, different types of errors and different things each aligner is good at. And our tool takes advantage of this. It combines the outputs of the other aligners, and it can use different settings based on desired output, in effect, to be tuned for precision or for recall or for F-score. And by doing this, we can outperform the individual aligners. In our paper, we focus on the English-Icelandic language pair. This is the first work focusing on word alignments for Icelandic, and thus we had to create dev and test sets. I will describe them in a bit. But even though we chose to focus mostly on one language pair, we also evaluated our system on 3 other language pairs in order to be able to compare the results to the results of others. We also experimented with different data availability by training or letting the IBM model-based aligners run on different number of sentence pairs. The paper contains a big table showing the results of that. So if you want to see those results, I'll just refer you to the paper. And the idea with these experiments with different data availability is to get an idea of how well the system copes with low resource scenarios, to see if that seems to affect the results. So, one slide about the reference set for English Icelandic. We manually aligned 604 sentences, randomly selected from the Parais corpus, which is a parallel English Icelandic corpus. Two annotators aligned all sentences and then checked each other's alignments and tried to get to an agreement on things that were different. These sets were split into dev and test sets. The dev set has 220 sentences and the test set has 384, or sentence pairs, of course. To help us do this, we built a simple tool that runs smoothly on Linux and almost smoothly on Windows. The tool is available in GitHub. The URL is in the paper. And back to aligning. To try to find the best combinations, we tried 5 alignment models, the 3 IBM model-based aligners mentioned before, and 2 sim-align models, one using MBERT and the other using XLMR. So MBERT is multilingual BERT. We start by running all aligners separately and try to find the best settings for each and every one by searching for the best parameters using grid search. Because the IBM model-based aligners learn probabilities from the data they run on, they should be better able to induce lexical translation probabilities and probability distributions when the size of data increases. So in order to study this effect and perhaps gain some insight into how our system would cope with low resource pairs, as we mentioned earlier, we also run the aligners using various number of parallel sentences to learn from. For the English Icelandic language pair, we tried everything from using only the sentences being tested and scored up to using over 3 million sentences and with 12 different steps in between. So for the other language pairs, our range was a bit less, from 0 to 500,000 sentences approximately. We then select the best settings for the different aligners and do a grid search again for finding the best ensemble methods. Having done our experiments, we find that in low resource scenarios, a combination of 3 alignment models, FLOMAL and the 2 unsupervised sim-align models, gives the best results. So, and when more data is available, the other 2 IBM model-based aligners become more accurate, and as a consequence, they are more useful in an ensemble. We thus report on 2 different ensembles. The smaller one combines 3 alignment models, FLOMAL, and the 2 sim-align models, and just require 2 out of the 3 models to agree. And if they do, the alignment is accepted. For this ensemble, which we call ensemble small, for sim-align we use the alignments produced by ITRMAX, which is an iterative algorithm introduced in the sim-align paper. This has higher recall, which is an advantage when only one of the aligners is allowed to miss an alignment. Ensemble large combines all of the 5 alignment models we tested, and for each of the individual aligners, we aim for the highest precision. Again, here we require a majority vote to accept the alignments, and this results in a model giving the highest recall and highest F-score. This can all be tuned and tampered with depending on the data you have and what your aims are. For example, if you loosen the requirements for ensemble large and accept a union of all alignment suggestions, the recall reached over 99%, but at the cost of precision, of course, which went below 80%. And the same applies in the other direction. If you want very high precision, it can be raised at the cost of recall by demanding more aligners to agree. And we managed to reach over 98% precision when demanding that 4 of the 5 aligners agreed. But both of these methods are detrimental to the F1 score. And in the paper, we only report on the results giving the highest F score. Our results, we can see them in this table. These are the results for the English Icelandic language pair. That the best results have quite impressive precision recall and F scores. These were obtained using ensemble large, training on 3.6 million sentences and selecting all alignments that had a majority vote, that is at least 3 out of 5 aligners agreed upon. For the other 3 language pairs, We use the same hyperparameters we trained for Icelandic, but used a different number of sentence pairs for training. This results in scores outperforming previous aligners, as it did for the English Icelandic language pair. The difference is maybe not so big everywhere, but it's a bit slightly higher at least. To see if our word alignments could be of help in a classic setting, we trained Moses, the SMT system, using our alignments or our alignment ensembles and compared to GISA++. We inspected the phrase tables. They were a lot smaller using our alignments, but correctly translated phrases were still there. So what was removed were the faulty ones, mostly. And when translating using this, we obtained slightly higher blue scores. The difference was quite small, below 1 blue in all experiments. We manually inspected the translations by selecting the better one out of 2. So in many cases, the translations were exactly the same, but not always. When using our ensemble, they were better in 23% of the cases, but with GISA++, they were better in 17% of the cases. So again, slightly better results, but maybe not a great difference for SMT. Finally, we consider, or what we consider our main contribution in this work is that by using, or we show that by using a combination of selected word alignment tools, it is possible to obtain high quality word alignments and outperform the individual tools. We have also published a new gold standard word alignment reference set for English Icelandic, which will hopefully be used by others in future word alignment work. We also created a small graphical tool for manually curating word alignments, and we have made that available under an open license on GitHub, as well as the source code for running the alignment tools and extracting combined alignments from them, the CombAlign code, which is also available under an open license. There, as usual, there may be some room for improvement. For example, if we would pre-process texts before running the probability-based tools or the IBM model, IBM alignment model-based tools by part of speech tagging and lemmatizing, the outcome could potentially improve. We would not do this for the contextualized aligners, only the statistical ones. It would also be useful to compare misalignments per aligner in order to see what kind of misalignments each aligner is doing in order to better select the best alignment candidates. And adding more aligners could also be helpful if we have good aligners, other good aligners. We are planning to use the word alignments for bilingual lexicon induction. We believe they may be quite useful there. And would also want to investigate if by getting slightly better SMT output, we could possibly get useful back translations to augment NMT systems. Work has been done on using SMT output as back translations to help with NMT training, and maybe the marginally better translations we get here could be of some help. Finally, there has been some interesting work in using word alignments for assisting with NMT training, for example, by adding an alignment attention layer, and it would be interesting to see if better word alignments would be beneficial for such a setup. This concludes my talk. We should have some time for questions, so if there is something I could explain better, I'll do my best. Thank you.